3 mode buttons on a modern bridge control panel, AZ-Man, Cruise, and Fast Steering, dictate how an AZ-Pod behaves in the water. For the deck officer, steering is a push-button command. For the marine automation engineer, that same command triggers a cascade of intertwined hydraulic limits, nested feedback loops, and bidirectional power flows happening below deck. To safely commission and maintain these systems, we need to decode the electronic and hydraulic logic behind 3 specific operational states: fast steering gear mode, open and closed loop control, and the reverse power condition. Treating an AZ-Pod like a traditional mechanical rudder, assuming a steering command is just a simple mechanical linkage, leads directly to nuisance trips, system faults, and compromised vessel handling. Reliable operation requires looking past the user interface to understand the governing logic that dictates the machinery's response to those commands. During near-alongside maneuvering, a bridge officer might engage fast steering gear mode. This is a sustained hydraulic configuration designed to increase rotational agility in tight spaces. The baseline steering gear uses high-pressure, closed-circuit hydraulics. Up to 6 marine-approved hydraulic winch motors drive evolvent pinions, which engage a large slewing wheel to rotate the entire pod. When fast mode is selected, the system routes hydraulic flow to combine the outputs of multiple pumps in parallel. This doubles the oil flow, which directly doubles the steering rotation speed. This graph plots available steering torque against rotational speed, showing the baseline curve. As fast mode combines pump flow, the operating point shifts far to the right, doubling speed. But on the y-axis, this comes at the direct expense of available hydraulic torque. The physical consequence is straightforward. The pod rotates much faster to execute sharp maneuvers, but the hydraulic oil loses its mechanical ability to resist external shock loads from the sea. In a sheltered port environment where wave action is minimal, the sea exerts little transient force on the propeller. The loss of holding torque is an acceptable operational trade-off here. Offshore, in open sea transit, waves constantly hammer the propeller. The system requires maximum hydraulic torque to hold the pod steady against those impacts, meaning fast mode must be disabled. Faster rotation is a deliberate mechanical compromise, exchanging resilience for speed. Below the physical hydraulics lies the electronic control layer. The bridge commands the steering gear using one of 2 distinct philosophies. Non-follow-up, or NFU, is a strictly open-loop directional command. Proportional valves open and remain open exactly as long as the operator holds the button down. Follow-up, or FU, is a closed-loop system based on absolute targeting. The operator dials in a specific numeric angle, say 20 degrees port, and the automation handles the transit to that value. That absolute target is processed by the EMRI ASU 36X servo unit. The bridge telegraph outputs the target angle as a 10-volt DC sine and cosine pair to a comparator node inside the ASU 36X servo. To determine physical reality, a feedback sensor on the pod sends its own actual position signal back into that same node. The servo calculates an error delta, the exact difference between target and actual signals, generating a command that ramps up the pump stroke. As actual position approaches the target, the delta shrinks to 0, dynamically ramping down the stroke to stop hydraulic flow. This automatic ramp down is an essential safety feature. It bleeds off the rotational momentum of the pod before it can overshoot. The closed-loop architecture also provides a failsafe. If the target signal from the autopilot is lost entirely, the sine channel drops to 0 volts. The system interprets this not as a command to hold position, but as an instruction to return the pod to midships. Once the error delta hits 0, the submerged AZ-Pod locks into the exact angle commanded by the bridge. Follow-up control delegates responsibility for the pod's physical deceleration and exact placement to the ASU 36X servo. The principles of inertia and control apply equally to the main propulsion motor and its interaction with the vessel's physical momentum. During rapid deceleration, the system can enter a state known as reverse power. This occurs when the ship's forward kinetic inertia carries it through the water faster than the RPM speed commanded to the propeller. The hydrodynamic trigger is simple. The forward speed of the vessel forces water through the propeller disc faster than the blade pitch is driving it. The sea physically drags the propeller blades. This external force turns the shaft faster than the motor's internal electrical field is rotating. Fast-moving water pushes against the propeller blades, transferring mechanical torque backwards from the sea into the shaft. That mechanical energy transforms into electricity. Internal electrical vectors reverse direction, flowing upwards from the pod, through the cycloconverter, and back into the ship's main switchboard grid. The synchronous propulsion motor has transitioned into an active generator. This kinetic to electrical regeneration pumps active power back into a grid that may not have the load capacity to absorb it. To prevent a blackout, the vessel's power management system must immediately throttle the diesel generators to accommodate this sudden surge of regenerative power. The propeller operates as a two-way mechanical interface. Commanding a sudden deceleration turns the vessel's kinetic energy into an electrical grid management problem. The terms used on the bridge, modes, angles, and RPMs, are shorthand for the physical, hydraulic, and electrical trade-offs happening below deck. Fast steering mode sacrifices wave-resisting torque to prioritize maneuverability in port. Follow-up control relies on precise 10-volt reference loops to mathematically manage multi-ton inertia without destroying the slewing gear. And reverse power converts the ship's momentum into active electrical generation. Understanding these control principles allows an engineer to safely commission, operate, and troubleshoot the hardware propelling the vessel. You now command the operational glossary and the control philosophies behind the bridge telegraph. Next, we go inside the physical pod itself, examining the shafting systems, the two bearing load distributions, and the Kobelco seal arrangements that keep the ocean out and the lubricant in.